Okay, let's get started. It is my pleasure to introduce Professor Aryan Mokhtari to kick off the IFML seminar series. For this year, Aryan is, why are you standing so close to me? Aryan is a new father, so congratulations. But more importantly, he does, fantastic research in optimization, and he has many great results on, kind of the first, all those kind of beating state-of-the-art barriers for rates and optimization that have stood for many years. And he's going to tell us how he's broken another one today on some awesome new work relating optimization to online learning. So I'm excited for your talk. Thanks for coming us off.
Thank you, Adam. Thank you for the invitation. Thank you all for making the time to come here. Before I start, I just want to say one more minor thing is like, yes, it's fantastic that we got another renewal for 5 more years of IFML. So congrats to everybody. And on behalf of everyone, I want to say thank you to Adam for leading the effort. We're going to enjoy another 5 more years of fun here. Thank you, Adam. You asked me to say that. Okay, so let's just start a talk. So today I'm going to talk about accelerating non-convex optimization using online learning. It's based on joint work with Rosaline and Francisco, my students. And yeah, hopefully it's not too boring. Okay. So motivation, optimization is important, so we're going to focus on optimization. So I'm going to focus on a very standard problem. I'm minimizing the loss function f. The dimension of my optimization variable is d, and the problem is unconstrained. As basic, as simple as it gets. No stochasticity whatsoever. The only number to remember is d is the dimension of the problem, no constraint whatsoever. All right. So what do we assume in this talk? We only assume that the function is non-convex at some level of smoothness, and the only thing that we can hope for, the most basic goal that we can chase is finding a point that has a small gradient norm, let's say gradient norm less than epsilon, and we call it the stationary point. For obvious reason, we cannot solve this to optimality, so this is a reasonable goal to chase, which is what everybody is doing. Now, what I'm going to assume in this talk is that I only have access to gradient of the loss function, only first order information, and nothing beyond that, okay? So that's the setup. And the goal is to find such a point. So I bet you should ask me, like, what's special about this problem? This should have been solved, and you should know everything about this very basic and simple problem. And hopefully within the next few minutes, you're going to realize that we still don't know a lot of things about this very simple problem. What we know so far is a classic result that if the gradient of the loss function is Lipschitz, meaning that this condition holds with some constant L, and if you run gradient descent type update, you can get to such point in 1/epsilon² iterations, or 1/epsilon² queries to the gradient. Okay, this is an upper bound, and in fact, it's known that it was shown in relatively recent results that it's optimal, and you cannot beat this. And gradient descent is optimal up to constant, so there's no room for improvement. So that's not good, or at least for people who are looking for a new problem. It's not good.
When you say worst case optimal, worst case over what?
Like there always exists a function that no matter what you do, you at least need 1/epsilon.
So worst case over the function.
Right. Good question. All right, so there's no hope for improvement, and the important thing is this lower bound is dimension independent. Like no matter what the dimension of the problem is, you always need this many queries to find such a stationary point. So there's no room for improvement. All right. What if I give you a little bit more assumption? What if there's some more structure to the function? Your query is the same, you only see the gradient, but what if I assume that the Hessian is also Lipschitz, right? So the operator norm of the Hessian between 2 points is related to the distance between those 2 points. If that happens, can we do something better than 1/epsilon²? All right, and this question was, sort of like attacked by 2 different groups of people, and they showed that it's possible to improve gradient descent and get something better than 1/epsilon². Funny thing, I vividly remember these 2 papers. I was still grad student, not long ago. Actually, it's long ago, it's 8 years ago. So, and these 2 papers came to archive the same week. Completely different idea, and they both got 1/7 to the power 7/4 log 1/7. Okay, so you see the improvement. 2 is now 7/4, which is nice. And they did completely different, two different approaches to get to this result. One was led by Elad Hazan, Tenguma, and their collaborators. They showed that if you approximate cubic regularized Newton method using, matrix vector product and try to do the Hessian vector product approximation using only gradient queries and Hessian vector product approximation, you can get to this. So it's an approximation of cubic regularized Newton method. I don't want to go into details, but it's just giving you a high-level idea of what they did. This one is sort of like more clever construction, in my opinion, by Yair Carmen, John Ducci, Oliver Hinder, and Aaron Sitford, that they showed that if you use a very clever way of using accelerated gradient method or non-convex optimization, you can actually get something of this complex. Completely different ideas, very complex, very, very complex algorithms, and very, very complicated analysis, especially for this one, for the second one. All right. So that's good. 7/4, that's improvement. But as any other optimization in problem, the question that we had is that, is there any way to improve it? And there was this relatively recent result in 2022, that they just come up with a restarting scheme on top of the second paper to shape the log factor. Okay. So they managed to shape the log factor using some smart restarting technique, and they got the complexity to the clean 1/epsilon to the power of 7/4, no log. And at this point, this is 2022. So after 5 years, this was the only progress on shaping a log factor. But the question was, is the 7/4 fundamental, right? Is there any way to improve it? I'm going to discuss the lower bound for this problem in detail toward the end of the talk, but just as a, like a side note, the only lower bound that we know for this problem is 12/7. So 7/4 is the upper bound, 1/epsilon, 12/7 is the only lower bound that we know. And there's a significant gap. I'm going to discuss this in detail toward the end of the talk. But my question was, can we improve the 7/4? Okay, so that's the problem. Yes.
Just to clarify, sorry if you already told us, but these algorithms, they only access the gradient, but not the second derivative.
That's a very good question. This one only accesses gradient. This one accesses Hessian vector product. So you can approximate Hessian vector products using gradient. So yeah, but no access to the Hessian. Yeah, but this is not exactly the same as the setup that yeah, but yeah. Not exactly querying the Hessian. All right, so what did we get? I'm going to go over that in detail, but like we showed that if the gradient is L1 Lipschitz, the Hessian is L2 Lipschitz, we can find such points in this many queries to the gradient. So there's a d-dependence showing up, 1/4, and the exponent is 13/8, and it's not hard to see that 13/8 is better than 7/4 because 7/4 is 14. Cool. But the caveat is that we have a d-dependence, so it's not dimension independent. But you can easily see that if d is less than 1/√epsilon, this is probably better than the previous. So at least in moderate size dimension regime, like we can get provable improvement over 7/4. All right. So the main idea is we're going to see two online learning problems that are going to pop up, and we're going to solve them and construct an algorithm. And the first problem is basically relating the task of finding station point of a non-convex functions into an online convex optimization problem of a linear loss. We're going to borrow some of the results by Ashok and his collaborators from this ICML paper. And then the second online learning problem is associated with the optimistic quasi-Newton method that we are going to propose, where the update of Hessian approximation itself is an online learning problem in the space of matrices. So this is the high-level idea of what you're going to see in the next 35 minutes. All right. So when I give a talk, I usually aim to answer 4 questions. And I think every talk should answer these 4 questions. What's the problem? What is the best known bound previously or the best known result? What's the new result? And what's the approach that you get to the new result, or what's cool about that approach? So I've answered the first 3 questions. We want to get to a station point of a smooth functions. The best known previous bound was 7/4, and we managed to get the exponent to 13/8. So the rest is going to be about how we get this, and hopefully there's going to be some, cute nuggets here and there for you guys as well. Right.
So there are 2 kinds of stationary points, right? One which is the local minimum, another one which may be like a saddle point. And
we don't have any guarantee.
There's no way to go to one faster or something.
That's a different question. So you can say that, okay, if I want to get to secondary stationary point that is epsilon's secondary stationary point, what's the complexity for that? Which is a different one. But here we're just saying that getting to any stationary point. And all the lower bounds and upper bounds are not just for any specific type of a stationary point, but we know that it can be local mean or saddle point or something. That's another question. Like, okay, if I want to get to a point that is approximately local minimum, like meaning that the gradient is small and the eigenvalues of the Hessians are not too negative. There's a whole line of work on that, the complexity bound for that, and so on. But here we just focus on norm of gradient listeners. Yes.
Just a clarification, compared to the previous known bound yours as a dimension.
Yes.
And the ones before they did.
No, they didn't do that. And that's why I'm saying that you're better when B is less than 1 over root x. Are we cool? All right, I bet you all know online learning, but just I gave this talk at a place that I wasn't sure if they know online learning, so I had this slide. So you know all online.
Where was that?
That was a yeah. I'll tell you later. It wasn't a tech place, or academic place. Anyway, so you're playing an online learning problem over the constraint set C, and you play it for T rounds. So you play action XK, which is from the feasible set C. And then after playing your action, you see your loss LK, right? And then your regret with respect to competitor X is the cumulative loss of your actions over the sequence of functions minus the cumulative loss of that fixed action, right? So I think you all know that, but just for sake of notation, this is what online learning is. And right, so now let's get back to our problem. So I wanted to find the station point of a non-convex function f. I'm going to show you that it can be written as an online convex optimization problem. Something that we know how to solve it and it's very tractable. And it comes from a very simple observation. So any optimization algorithm that you pick, almost any, can be written as this. You have a point xn minus 1, you want to pick the next point, and you pick some descent direction or some step direction, whatever you want to call it, right? Delta n. And without loss of generality, I'm going to assume, the only thing I'm going to assume about it is that it has bounded norm of D. Okay? Just for the sake of argument. All right. So if this is my update, what's your goal for picking delta n? Your goal should be like, I want to pick this delta n in a way that I maximize the amount of function decrease. Very basic optimization way of thinking about the problem, because I want to decrease the function. So among all the directions that have norm D, pick the one that maximizes the function value, right? And then the question is how you would pick that, right? Well, it's not that hard to see that if I use fundamental theorem of calculus, the difference between function value at xn and xn minus 1 is exactly the step that you have taken, xn plus 1 minus xn, times the average of gradient over that segment. Is there any marker here? No. No, apparently that's frustrating. Anyway, so basically what is this delta n? What is this nabla n? Basically, nabla n is the average of gradient over the segment of xn minus 1 and x. So if I knew this animal, right, the best thing to do would be what? Would be picking the direction that is exactly the negative of that with norm D, right? That should give me the maximum function decrease. Why don't we do that? Why nobody has done that? Because finding this nabla requires the knowledge of next point that you don't have access to, right? I'm at xn minus 1. I want to pick my next step to go to xn, but the best step depends on xn, right? So that should bring up online learning to your mind when you think about it. And then the other important thing is like you have an integral. Who wants to take an integral over a segment? You know, nobody likes even computing two gradients. So anyway, so nobody wants to compute an integral over a segment. So what are the ways that
You
we
can sample, I mean, you can do sample.
What's that?
You can do sample.
Absolutely. That's one way to get rid of it, but there's a simpler way to do it. I'll show you.
But there will be an implicit Euler method.
Yeah. But still, you need to know the next step to figure out the segment, right? I don't even know what the segment is, right?
That's exactly.
Right. All right. So what do we do in optimization? We just say like, screw it. Like I know the current point. Let's use the current gradient as the estimation of the sole gradient over the segment, right? And that's what we call it gradient descent, right? The only difference is since I'm bounding the step size, it's going to be like ending up with something like normalized gradient descent. So you take the gradient direction, you normalize it by the norm, and then take a step of size d. All right. So that's a natural way to get rid of computing the integral and not depending on the next iteration, and everything is known at the current time. Cool. What's the problem? You can show that the amount of function decrease is going to be bounded, but depends on the first level of smoothness of the function L1 and the distance of the 2 points squared. And if you do the math properly, And it's not hard, honestly. It's going to be very similar to analysis of gradient descent. And you're going to get 1 over t squared, 1 over root t, which is 1 over epsilon squared. So this naive approximation of the gradient over segment will just give you a variant of gradient descent that is not better than 1 over epsilon squared. Nice, but that's a good attempt, right? But what if I tell you that the Hessian is also Lipschitz? Maybe you can do something better to approximate this average gradient over the segment. And that's actually, Adam, something even simpler than the sampling. You just pick the middle point. If you pick the middle point between xn and xn minus 1 and compute the gradient at that middle point, it's pretty good. It's a pretty good approximation of the whole segment. And you can show that the error of that gn being the gradient of the middle point is off from the true gradient of the whole segment by something order of delta n squared, if you have second order smoothness. And that's a key. All right? And that level of error is affordable for us in the analysis. Okay? So I can just use the middle point.
So the smoothness that gives you the middle point.
Right, right. But you just need one, that's where I'm using this additional assumption that you can go beyond the barrier of gradient. Yeah.
But I still don't know the next point.
Exactly. Yeah. You're speaking my language. Yeah, I just solved one problem. I solved the problem of integration, right?
Oh.
But I still have to know the next point to compute the middle point, right? I don't know that, right? Well, assume there's a genie that can compute that for you. What's funny, if I go to, and with this approach and pick the middle point and do the analysis, I'm not going to bore you with the analysis. You're going to get t to the power of 2 over 3, which is 1 over epsilon to the power of 3 over 2. Very good bound. Epsilon squared, 7 over 4, 3 over 2. But again, the problem, as Sanjay said, I still cannot do this algorithm because I need to know next, right? But the catch here is like, it's very much related to online learning problem. You guess what's going to be like, you play an action and you see how far you are from the middle point that you would have wish you had. And then you correct your action. Hopefully over time, it's going to give you something nice, right? So that's basically the analogy that they use to come up with this non-convex to online convex optimization reduction. So basically what you can show that is the amount of function decrease is something like this. You know, how good you are compared to the Gn is the gradient of middle point, and then this is the error that is coming from the fact that you don't have the exact integral, right? If you had the exact integral, this would be equality and it would be respect to naught. But if you just add and subtract this Gn transpose u, Gn being like the gradient of the middle point and u being an arbitrary fixed action, with some massaging the terms, you can show that if the competitor is the average of gradients, is the sum, if the average of gradients of these middle points, or t iteration, suppose you play this game for t iteration, you play these actions for t iterations, and you can show that the amount of function decrease is bounded by something like this red term plus the blue term plus this additional error that comes from the sort of discretization error. And now you can pick any u that you want as your competitor. Now, if I pick u to be the average of the middle point gradients, and it has to have norm d because it has to be a feasible point, then it pops up in the left-hand side as the average of gradients of middle points.
Sorry,
Yes, sure.
Can you repeat exactly what Gn is once more?
Gn is the gradient of middle point.
It's the online algorithm has a very strong guarantee to be competitive with any sort.
Yeah, no, he was asking what is Gn? Gn is the gradient of the middle point.
But in particular, he's choosing like when say in particular, I'm going to be competitive with middle points, even though I don't know it.
Right.
So, okay, that's what I was asking you. So Gn is the true middle point, not your
Yes.
guess of the middle point.
It's
Okay.
no, it's
That's
the
what
true middle
I was trying to
point.
resolve
Yeah.
immediately.
Right, right. I have not given you any algorithm so far.
Okay.
All I'm saying is that suppose I'm playing this game. Xn minus 1, delta n, I see xn. Xn minus 1, delta n, xn. And I haven't described how I pick delta n. For any delta n, you can come up with this guarantee. That your that your function decrease after t iteration is the accumulation of this term and this term, which you can think of this as regret. Where I play delta n, and I hope that it was aligned with negative of the gradient of middle point. And that's my cumulative loss. And u is the best fixed point action in hindsight, which I'm going to, like, not the best one, like a competitor. I happen to pick that competitor to be the average of the gradients. Right? Yes.
Delta N has bounded north, right?
Yes. Yeah, I'm picking all my actions from a feasible set that has bounded norm, and that's why u is also has a bounded norm of, right? So what does this result mean? This is just a constant. Time is the horizon. D is the set of, the step. This is also not a constant, but this tells me that whatever delta n's I pick, if I manage to make this sum small, I'm going to end up with a point, average a bunch of points, that average a bunch of gradients that they have a small number, right? But this is average a bunch of gradients. I don't like average a bunch of gradients. I like the gradient of some point, right? Because I want to output a point, not average a bunch of gradients, right? So you have to relate the gradient of the average of this t episode gain, right? Suppose W hat is the average of all the middle points. I'm showing that the gradient of that is not far from the average of gradients. And if you put it back into the previous bound, you get this simple, nice expression. And you can easily see everything in this picture. Again, I have not described anything about delta time. At time 0, I play some delta 0, I see x1, and then all the way to xt, and I play delta 0 all the way to delta t. I'm saying that if you play this game,
Wait, I'm just a little lost, Penny.
No?
You write that lemma.
Yeah.
On the left-hand side is an order 1 quantity. It's the right-hand side, you have an average, but then there's a t-square on the last thing. Won't that swamp everything, or I'm missing something?
no, it's completely correct because it's coming up related to the second order of a smoothness, and the second order of a smoothness has something to do with the distance squared. And the distance squared is going to give you something like d squared t squared.
Bound useful because one side is going to blow up in t.
That's a key, like because I can control d. But that's a good observation. That's a very good observation that you have. Like if the horizon becomes very large, then I'm going to pay the penalty here, right?
Yeah.
So that's why there's going to be another slight effort. So I'm going to explain that. But anyway, the important thing is this reduction that if I look at the average of these middle points, the gradient of that is bounded by this animal. 3 constants and an online learning problem that is linear, right? I keep playing delta n's and I suffer this loss and I compare against this competitor. All right. But as Sanjay said, when t becomes large, we're going to have a problem. This time it's going to blow up. So what we're going to do, we're going to play a multi-episode game. So every t iterations, I change my competitors. And then I'm going to have k episodes of that, right? So to make sure that t is not too large. And if I do that, it's not hard to show that you can get something like this. You're going to have t squared, which is the size of the each episode, but it's not going to be the runtime because the runtime is t times k, where k is the number of episodes that you have. So this way you can control the error of replacing the average of gradients with the gradient of average, right? Does that make sense, Sanjay? Just some technicality to control the parameters. It's just giving you one more degree of freedom, basically. Because, yeah. All right, so all in all, the important thing that to have in mind is that after this process, no matter what delta you pick, the output of this procedure would be the average of the middle points. And I can guarantee that the gradient of that is bounded by this. And the only way that I can improve the upper bound is by playing this online game as good as possible to get a small regret bound. If I get a small regret bound, the upper bound is better, I can choose these parameters better, and I get a faster. Are we good? Yes.
In the previous slide, was it for any U or for U as?
No, for the U that I described.
Okay,
It's not for any U. I fixed the U. Yes.
so the point is like this U is in general doing well and then I want to.
Yeah, exactly.
Okay,
I just pick one U that gives me a reasonable output with a reasonable approximation error, so I'm going to go with
how
that.
did you decide that this is a reasonable, just from the analysis
Yeah.
that popped up?
Yes.
Something again, my intuition is bothering me here. You have t times d, but both are the same power, t squared, d squared.
Yes.
D is the amount you can move per step.
Right.
T is the number of steps. So since they're bounded, how can you play a game? You can't move too far. The amount you can, if you make d too small, you need a large t to move certain amount.
Yeah.
So you're not getting a gain.
No,
See what I'm saying?
it's about these are two parameters of your optimization problems, right? I can pick how long is it horizon, and given that I can pick my step size, right?
So
If I see the horizon is
Let
very
me
big,
define-
I should pick a smaller step.
let me define my question. Suppose I want to move a distance r. Okay. Then if I need to take d and t to be inversely proportional to each other.
No, I don't.
Which means that I can't, by playing any games that.
Let me put it another way. Suppose you fix D, and I know that each time I'm taking this many steps, right? And then I know that after this many steps, the error between the average of gradients and gradient of average is order dt squared. So given that, I'm going to pick my horizon to be smaller so that I can do this.
Play and reset again and again.
Yeah, exactly.
That's reset again.
Yeah.
That's what it's called.
Very cool.
Yes.
So that was the first online learning problem. So the task of finding a solution point of a non-convex function can be boiled down to solving an online learning problem with a linear loss, which we know how to solve it perfectly. All right. Cool. Now, You should ask me, okay, now Aryan, from now on, everything should be trivial. We know how to solve this problem. You do projected online gradient descent, you do FTRL, boom, boom, you get the root T and you put it there. Why not? You can do that, absolutely. You're going to get garbage. Your complexity is going to be 1 over epsilon squared again or something even worse. The key thing that you have to observe and leverage here is that when I take an action and I see the gradient of the middle point now, the gradient of the next middle point is not arbitrary technically, right? Because we're dealing with an optimization problem and the smoothness and the stuff. So I can sort of like predict or like control how different the next gradient is going to be, which is the main difference between classic online learning and the problem in hand, right? Given this structure that I can control what's going to be next, it's reasonable to go with an optimistic framework to solve your online learning problem, because optimistic framework is useful when you can leveraging the smoothness of the loss to do something about predicting what's the next grade. But you're all familiar with that, but I'm just going to give you a very short introduction to the optimistic method for solving online learning problems. Again, suppose Gn is the gradient that you want to compute, which is the gradient of your loss at time n, and Hn is some hint that you have access to, given all the information that you have seen so far, right? And then the whole idea of optimistic method is that if the error between Gn and Hn, the true gradient and what I estimated at time n, and n minus 1 are close, then it's a good idea to predict the next gradient to be my current estimate plus the error from the last iteration. So this is your prediction, this is your correction. That's the way to think about it. All right, and I haven't described what is Hn yet. For any Hn, you can use this way, right? And if I happen to use optimistic method, which is basically following this update, so your step instead of being the negative of gradient of the current point or anything like that, is like basically approximating Gn by this animal, and this would be your update, and then you project to the ball of size d. So this is how I'm going to update deltas. If I go with this approach for updating my deltas, then I can show that the regret is something that you can replace by, as you expect, the difference between the true middle point gradient and your estimate of the true middle gradient. And there's this nice negative term that is showing up, which is showing the distance between two consecutive steps. All right. So what did I say so far? I didn't describe anything about the algorithm. I said you just do some delta n's, right? But the delta n's happen to be following this approach. Previously, I didn't have any update on delta n's, but now I'm saying that delta n's are going to be updated this way, but I haven't described Hn, right? So there's no algorithm yet. But if you pick any hint function, you're going to get this upper bound. So of course, you want to make this as small as possible for the same reason. Then the regret becomes a small, and as a result, the upper bound becomes a small, and all those things. Are we cool? Not too bored yet? All right, so all you want to do is to pick the right hint function for the middle gradient. All right, so suppose I played at time n minus 2, I played delta n minus 1 and I got xn minus 1, and now I can see the middle point wn minus 1, right? Now my goal is to predict the next one, the gradient of the next middle point. What's the most natural thing to estimate the next middle point gradient? Is to use the current middle point gradient, right? That's the basic first order optimistic method, right? And if you do so, you can show that the error between your estimation, which is the previous last point gradient, and the true one, which is the gradient of Wn, the difference is something depending on the delta n minus 1 and delta n divided by 2. Even the picture shows that, roughly speaking, and L1 pops up. Now, if I replace this animal into my previous upper bound that I had here, right? And optimize for D, optimize for T, do all the mumbo jumbo magic that I'm going to do, I'm going to get 11 over 6. Okay? So I use this hint. I replace this error by L1D. Now I get something for the regret, right? And then I put the regret bound in the original bound, then optimize for D and T and all these parameters. I'm going to get 11 over 6. Better than over epsilon squared, but worse than 7 over. So that means that your hint function was not good enough. All right. What if now the clever idea here is that how to come up with a more efficient hint function for the optimistic method. So we came up with this idea of doubly optimistic approach, which basically we're saying that, okay, at xn minus 2, I played delta minus 1, I saw x minus 1, and I got wn minus 1, which is my middle point. What if The next step is also very similar to the current step. What if I was keep going this way? Then this animal would be my middle point, and this would be my extent, right? So I'm approximating that my delta and delta n minus 1 are also close to each other. If I go with that hypothesis, I would use this gradient as the prediction of this one. Right? That costs you one more gradient calculation per iteration, but who cares? That doubles up everything, right? But I'm going to predict the next gradient, Hn, to be the gradient of the next middle point if delta n and delta n minus 1 were the same. And you might think that's a very weird way of thinking about this, but it actually makes a lot of sense because now the error of your estimation should depend on how much delta n is different from delta n minus 1. Because if they are close, my approximation was perfect, right? And why this is better than delta n plus delta n minus 1 that I had previously? Because of this bad thought. This negative term is going to save me. I can afford to have an error of this form because it's going to be canceled by this term. So this addition, this sort of like new hint has an error that is related to delta n minus delta n minus 1. And I can absorb this error with the negative that I have, and then I can get a better regret. So if I put this into my bound and write the regret and put the regret back into everything and optimize for D and L and D and T and everything, I'm not going to bore you with that. Guess what you get? 7/4. The best known bound. What's the algorithm? There's 3 lines. As simple as that. At time n, I play delta n. Let's say you have from previous round. And then you compute the gradient of middle point. And then the gradient of middle point between xn and if you were going with delta n, right? And then this is your update. The optimistic method, first order, nothing beyond gradient. And given this whole argument, actually the proof is not more than 2 pages. Because it's all based on this, all the reductions that I told you, and then the regret bound is very easy to put together. So this algorithm, very simple algorithm, would give you 7/4. And it's basically a doubly optimistic hint function, if you wish. Any question?
Where do you use the smoothness of the Hessian?
That's a great question. Sorry, right here, please. There are 2 places. First place was when I was replacing the integral with the middle point, if you remember that. That's one. The other one is actually, I think that's the only one. I'm going to use it for quasi-Newton. For the first order, I don't use it anywhere in this part of the optimistic method. Everything is L1. Yep. But I'm going to use that in the next step. So what's important about this result of this part is that I think it's a very, very, very simple algorithm to give you 7/4. It opens up the door to think about, is there any way to get something better than 7/4 if you improve your hint function? So we got this, we were happy, but we were like, okay, we want to beat still 7/4. Is there any way to do better than 7/4? And then naturally, should be something related to how we build your hint function, right? So now suppose I tell you that you have access to the Hessian. If you had access to the Hessian, what would be your hint function? It would be the gradient approximation around the next middle point that you're predicting and using the Hessian for that middle point, right? So if I had access to Hessian, the right hint would be instead of like using the gradient of the next middle point that you're approximating is like the additional term of Hessian times its linearization. If I had access to the Hessian, that would be the right hint function. And now I can use the L2 Lipschitz continuity Sujay to show that your error is now in fact even smaller because previously I had L1D. Now I can get L2D squared, and as a result of this better approximation error, because these steps are small, D is small, I can actually get 1/3/2. So if you had access to Hessian, you would get 3/2. This is optimal for second order methods. So if you have access to gradient and Hessian, gradient Lipschitz, Hessian Lipschitz, you cannot beat this one. This is another yet interesting result by itself because the algorithm that achieves this complexity is cubic regularized Newton method. It's a messy algorithm, requires solving a solved problem that is nasty, but this is just requires solving a truss region solved problem, which is much easier. Anyway, I'm talking too much, but I'm just saying that this is optimal if you had access to second order methods, second order information. So this gives us the hope that this seems like the right direction for the hint, because if I had access to Hessian, it would give me the optimal rate. So what if I don't have access to Hessian? like any other papers of mine, like you just replace it by a matrix B, right? And then you try to figure out what's the right B. B is an approximation of the hash, all right? So the catch here is that still because of the linearization, your H depends on delta, which is the next point. But that's fine because that's a linear operator. And you can think of this as basically when you put this hint function, if that's my hint, I'm replacing the Hessian by B, then the update would require solving basically a quadratic problem over a constraint set, right? Because I have a quadratic, like you can write this problem as this is, which is known as trust region methods. Because you have delta n plus 1 here, right? Because that's coming from the linearization at the next one. Anyway, but you can cast this as a quadratic problem over a L2 norm. And if it wasn't this, you can just do the inversion. It was easy, but with this, it's you're dealing with the trust region subproblem, which are so many efficient methods to approximately solve it. And I'm not going to get into the details of that because it doesn't add anything to my gradient query. I'm going to talk about the computational cost of solving this subproblem. But to run my update using this hint that I described, all I have to do is to solve the subproblem like this. All right? And you don't need to solve it exactly. You need to solve it up to sub-approximation. There is some detail. I'm not going to bore you with that. But now the big question, the second question is that, okay, we know the hint. Now how do you pick the B, the approximation of the hash? All right, so we're going to do the same thing. I'm not going to assume anything about the B. I'm just going to let the analysis tell me how to pick B. So if I go with any B, right, I can show that the regret would be bounded by this upper. How did we get to this bound? It's irrelevant. But the important thing is, like, if I go with that hint function and B is an arbitrary matrix, I can show that the regret after k steps would be something dependent on yn minus b and Sn. Sn is the difference of two different steps, two consecutive steps, and yn is the difference of the consecutive gradients. Now the question is, how should you pick Bn to make this term as small as possible? Yes.
Aryan, why isn't this part just a black box of your previous paper?
It could be related to that. It's not exactly black box, but many ideas are coming from that. Yes. Yeah. Because like the fact that the regret boils down to something like this is because the hint function that we have here is not exactly the same as the HP framework that they had previously. But there are connections. That's why I'm not going to go over all the details of that. So basically, I can show that the regret would be depending on Bn this way. Now, you should tell me how should I pick Bn? Of course, you should pick Bn such that you make this sum as small as possible. The catch here is, I don't know Bn. I don't know Sn and Yn when I'm picking Bn. So basically, you pick your Bn, then you come up with your hint, then you see the next one, then you see the difference of gradients, then you can see Yn and Sn. So that's another online learning problem, but now it's in the space of matrices. And the loss function is going to be quadratic, not linear. So basically, it's not hard to show that the problem of selecting B boils down to picking a matrix that has operator norm less than L1. The loss is going to be this quadratic thing. And I just want to minimize the cumulative loss because that's exactly what shows up right here. All right. As Sanjay said, we have seen this show before in some other papers of mine with Roichen and Chujan. And for simplicity, I'm just going to assume that we are using projected online gradient descent to solve this problem. We don't need optimistic methods. Even this would give us a reasonable bound because the function is much nicer than linear. It's quadratic. And we can show that if you do dynamic regret analysis, not a static regret, there is a sequence of HNs for which ln HN is small. And if you put all those things together, you can show that ln BN, I'm not going to bore you with that. ln BN is bounded by something like this if you follow the online gradient descent update. And that's where the small d pops up because you have an error term that depends on B1 and H1, which is a standard in online learning analysis. And the only way that you can bound it is that with some form of d dependence. That's why small d pops up, the dimension of the problem. So if you just solve this problem using online gradient descent, you would get such cumulative loss for ln BN. If I put it back in the regret, I get some regret. And if I put back regret into this bound, all in all, I would get this angle. All right. So if I go with this doubly optimistic method and I update Bn using the online learning problem that I told you, I would get this upper bound. And this is the moment of truth. That's the moment that you optimize for T and D and everything. And you hope that the right-hand side is going to give you something nice. And the good news is it gave us something nice and it gave us something that depends on D and M. But if you do the epsilon complexity, you're going to show that you're going to make this right-hand side less than epsilon if you run the iterations, the algorithm for at most d to the power of 1 over 4 over 1 over epsilon to the power of 13 over 8. which is the bound that I promised. And as I said, this is better than the previous bound if d is less than root epsilon. All right. So basically, there are two online learning problems that you have to solve. You construct the algorithm, and the algorithm is basically nothing except this. So you have delta time, you pick the next point. The next delta time plus 1 is going to be solution of this first region solved problem, which is a quadratic subject to norm constraint. And then you update b using this. There are so many details that I basically didn't cover. Number one is I didn't mention how to solve this first region solved problem. How is the cost of that? That's a side note. The second thing is I don't actually use the projected online gradient descent because now you have to project in the space of matrices. That is costly. That is d-cubic. You have to do the full eigenvalue decomposition to bring all the eigenvalues with such that the operator norm is less than L1. So we do a projection-free version of this that has a cost of order d squared. It's going to give you the same guarantee, but I'm not going to bore you with that. That's another 40 minutes of talk. All right. So one thing I want to mention is
Where did the D come? You know, D over epsilon. Where did the D come?
small d
Yeah.
right here. Because when I do the online learning analysis, the regret analysis for LNBN, right? Usually the first action minus x0 will x0 minus the first action will pop up, right? And that's a Frobenius norm of b1 minus h1. And there is no way to bound it better than L1 root d. And then you have the squared, so you get L1 squared. But you're doomed to pay the price of d.
So I see this approach here.
Yeah. I mean, if you know something about the Hessians, you can make this d independent. Suppose that if I tell you that the Hessian is low rank or has small energy, then I can pick my b to have that, and then I would pay s instead of d, s being whatever notion of low rank or sparsity that you want to have. But there's no assumption here. We're going with general bounds. Yes.
So there is a sequence of optimal B's that are all of rank 1, right? Because you only depend on yn minus bn sn.
Okay.
Like, does that help you at all that you would avoid this D dependence if you made them be ranked 1?
I don't think so, because still I have to look at the B1. Actually, that's a quick. But I don't know if that sequence is going to give me something good, right?
Well, there's always a rank 1 sequence that gives 0 or good, right?
I have to think about what would be the ln of Hn though. You have to think about this and this term too. Because there's another D that's popping up from this one too. I forgot to mention that. Because this is also the difference of two consecutive Hessians, right?
This comes from a different regresses dynamic.
Yeah, I have to do dynamic. There is no fix. Like we could not come up with a fixed competitor for which this, yeah. You had to go with the dynamic. All right, so I told you about the upper bound, which is 13/8, but then the question is what's the lower bound? It's 12/7. I vividly remember when we were on the board with my students, Francisco, and we got 13/8, and we were like, which one is worse, 13/8 or 12/7? And guess what? 12/7 is worse than 13/8. So we beat the lower bound. What the heck, right? Yeah. So we went over the board again and again. We saw 13/8 is correct, but then we realized that the lower bound in the original paper by Carmen, Ducci, Hinder, and Sitford is only true for high dimensional cases. When d is larger than 1/epsilon to the power of 12/7. Now, since we have a d dependence, if you replace our d to the power of 1/4 with this animal, you're going to get 1/115/56. And this is worse than 12/7. So good. That was a good moment, like really, like such a relief. So, but the question is, okay, we have an upper bound and there is a lower bound, but obviously the lower bound is not tight because we know that at least for a small d, we are better than the lower bound. So there should be another lower bound for lower dimensional case, and that's still open, basically. And we don't even know if the upper bound is tight too. So there's a lot of unknowns in this very simple problem that you might think by now it's all done or known. All right, so this is a final, okay, it's 1, so I'm not going to bore you more. It's just a final picture about the upper bound. So the previous bound was 7/4 in terms of epsilon. There was no dependence. We are right here. And this is if this is the complexity 1/3/2 if you had access to the Hessian. If you go with CRN or the second order method that I described. What I like about this plot and why I asked Rochin to put it here is like this is right in the middle. That's pretty nice. But we have a d dependence right here. So now the question is, can you go this way? You know, pay a worse d price, but get closer to 3/2, or ideally come this way and get both d and epsilon improvement better. that's pretty much it. I mean, for those of you who have seen my result for the convex, we managed to show a similar result for the convex case. Basically, we showed that it's possible to beat 1 over k squared if you run iterations more than 1 over root epsilon iterations. And so similar terminology can be extended to the convex case, and you can actually outperform accelerated gradient descent if you run iterations more than the iterations. Well, so it's time. It's 1. I'm not going to bore you more with my stuff. Thank you so much for your attention. And this is the paper that I created. These are the results for convex and strongly convex cases. Thank you.
If someone has a question for Aryan. Yes.
Yes.
So in general, like, for high dimensions, is the analysis loose, or is the issue with the method that maybe for high dimensions, online learning type of framing may not be like the best thing to do?
Well, the thing about the high dimension is that we still don't know. I mean, the dependence that we get in the quasi-Newton method, I think it's unavoidable because you're trying to predict the behavior of a matrix, right? So if you don't know anything, you have to at least wait for d iterations to collect some information about the columns of that. So that is fundamental in my opinion. But how does the d show up? In this case being 1 over 4, it does depend on your online learning algorithm. So there are arguments. I mean, again, going back to Adam's question, if I knew something more about the Hessian, or if I had some more assumptions, maybe I could have got a better regret bound where the d pops up. And as a result, I would get better dependence on d. But I would be very surprised if you can get a completely d-independent result to beat like basically 7 over 4. That's my guess, but it might be possible. Yeah. And about the lower bound, I mean, still there's nothing we know about the lower bound for a case that epsilon is less than 1 over epsilon to the power of 12 over 7 is less than, if d is less than that, basically. Unless d is order 1, then in that case, you can come up with some exponential lower bound, which is easy. All right.
Question, Thomas.
Yes.
I have 2 questions. Probably both are really stupid. So first of all, don't you get a lower bound that you can improve just by taking quadratic f? And secondly, the Lipschitz constants depend on the choice of the bound of the
Right.
Region. The larger you pick the region, the larger the Lipschitz constants. So how do you factor that?
These are good questions. So going back to your first question, you're saying that if I had access to Hessian, that would give me a lower bound, right? But that's under a different query. You assume that you have access to Hessian. But that's fair. It's unlikely that we should be able to beat 1 over 3 to the power of 3 over 2. But that's not necessarily a tight lower bound because that is achieved if you have access to Hessian, if that's your first question. The second question you're asking is like the dependence of all these parameters on how these parameters depend on L1 and L2. I didn't mention that, but actually your D, which is sort of like your step size, has to be proportional to all these parameters to get all the guarantees that I mentioned. M is basically D, this depends on D and epsilon, and then you have dependence on L1 and L2. So yes, if L1 is larger, naturally your step has to be smaller, and it does pops up in the bounds, which is kind of like a standard. Like as usually your step size is something related to 1 over L, but it's not exactly 1 over L in our case. It's a combination of L1 and L2, but it makes sense because if you look at the sum of the exponents, it actually adds up to 1. But it's a mixture of L1 and L2 squares. So it does depend. If the function is nicer, you can take bigger steps. But if it's like, like it's rapidly changing L1, then you have to be more conservative in selection of D. But no matter what, you can get this guarantee. But at the end of the day, L1 and L2 also show up in your upper bound. I just hide those dependence on L1 and L2, and I just highlighted dependence on D and epsilon. Because these are sort of the constants that I care about. Does it answer?
Yeah, I mean, if you take a quadratic function and consider its Lipschitz constant,
Yes.
and let's say x is smaller than 10, or x is smaller than something in a ball of a certain radius r,
Right.
then the Lipschitz constant will be proportional to r. Because the
yes.
further away you get, the larger is the Lipschitz constant.
Okay. So
So it will depend on how large the region for x is.
that's a fair, but like, I mean, we always have a global bound, right? I'm assuming that the function is globally L1 Lipschitz everywhere, which by the way, quadratic function is not.
Yeah.
Actually, it is, sorry. Right. Quadratic function is, Lipschitz, actually, right. But yeah, but that's universal. Actually, for quadratic function, right? No, actually, no. Yes. Quadratic is a classical gradient Lipschitz, and the Lipschitzness is the
So
same.
you said the second derivative is Lipschitz.
Both. Both the gradient and the Hessian are Lipschitz, both L1 and L2. They are both assumptions. But quadratic satisfies this. There's no problem with that. It's gradient Lipschitz, and the Hessian is not changing. So L2 is
The
zero.
gradient depends on the domain of functions as well.
No, but it's a universal bound for gradient. It's not like a to the power of 4 that gets worse when you get worse, right? It's a quadratic function. L1 is everywhere, it's the same thing. X transpose AX, you look at AX minus AY, it's AX minus Y, it's norm of A, it's everywhere the same. It doesn't depend on the radius. If it's higher order, yes, you're right. If it's like to the power of 4, yes, then the Lipschitz gets worse as the distance goes.
I see.
Any other yes?
Did you think that there's hope to get a better guarantee by setting up a different second online learning problem? Because the first one you said seemed pretty tight, given that if you have full second order access, you get the type 3 over 2. But can you look for better hints?
I bet. I mean, it should be possible. The reason that I was hopeful that this should be the right way to do it is that if I had access to Hessian, this would be the right thing. Right? And if I'm trying to do something that is mimicking high order, maybe that's the way to go. But you're right. There's no. And then the thing is, like, we did not try to do. I mean, I don't know. Maybe there is another way to come up with a hint. But if you want to follow approximation of this so-called second order hint, I think this is sort of a natural way to go because we did not pick B in any way. We didn't force B to be anything. We just let the analysis tell us how we should pick it. But maybe there's a completely different way of thinking about construction of the hint that has nothing to do with this linearization I'm talking about. That's a fair point. All right.
Okay, let's thank Aryan again. Great.